Hi, everyone. Thanks for having me here. So, firstly, I'm from Ireland, from the University College Cork, PhD researcher. So, all these analyses are still ongoing, just so you know. So, the title of my talk today is The Irish Seasonal Coastal Current, the Source of Muggaea atlantica in Ireland. So, Delphine teed my talk up quite nicely just there. So this is Muggaea atlantica. On the left, we have the polygastric stage, and on the right, we have the eudoxid stage. And in Ireland, we would consider this a harmful jellyfish. In this conference, we've heard a lot about the interactions between jellyfish and fisheries, but in Ireland, it's more so jellyfish and aquaculture. So these jellyfish are so small, kind of max 7 millimeters, they can drift into the cages of salmon farms, sting the salmon, sting their gills, reduce their immunity, reduce respiration, and this can ultimately lead to mortalities. And as my colleague Hannah spoke on Wednesday, abundances of Muggaea in recent years in Ireland have been very high. So last September, October, we were getting 3,000 individuals per meter cubed. And a harmful event, the threshold is about 200 per meter cubed to be considered harmful. So these are some really high abundances. The season for Muggaea in Ireland is around the end of July to the end of October, early November, so they're not present year-round. So where are they coming from if they're only a transient member of the plankton in Ireland? Well, there is a known resident population of Muggaea in the Western English Channel, indicated by the grey star on the map there. And work by my supervisor, Damien Haberlin, published in 2016, observed similar abundances with a bit of a time lag between the L4 dataset located in the Western English Channel and in Bantry Bay in southwest Ireland. And he suggested that there was a potential connection between these sites. But if so, what is this connection? Well, there's a well-described seasonal coastal current in the area that actually connects these two regions. So it's depicted by the orange color on the map here. As you can see, it flows from the west coast of France to the Western English Channel, across to southwest Ireland, and then up north, connecting with the coastal current in Scotland. And extensive research has been done on this coastal current concerning phytoplankton. So briefly, how does this coastal current form? Well, it forms quite close to the coast, and it forms only in the summer months in Ireland when the offshore Celtic Sea becomes thermally stratified. So basically, the sun heats up the water column. There's a lack of mixing in these offshore areas, and this creates a thermocline. So there's warm, buoyant water on top, a rapid change in temperature at the thermocline, and a cold, dense pool of water beneath. And this is a bottom density front which approaches the coastline. Then when we get to the inshore waters, they're a lot more mixed due to the action of the waves. It dissipates all this thermal energy. So when we get the mixed inshore waters meeting the stratified offshore waters, we get a bit of a surface front occurring. And there's kind of nowhere for the water to move. So what ends up happening is we get a perpendicular flow, which is our coastal current, perpendicular to this bottom density front. And due to the Coriolis effect and us being in the northern hemisphere, it is westward flowing. So it flows parallel to the coast. It's quite narrow as currents go, 5 to 10 kilometers, relatively fast flowing, especially compared with the surrounding water. So we're talking 20 to 40 centimeters per second. And what's more, large quantities of phytoplankton have been seen to be moved in this current around the southwest coast of Ireland. So our hypothesis is, if this current can transport phytoplankton, why not jellyfish? To investigate this, we were lucky enough to go out on a 7-day research cruise around the southwest coast of Ireland on one of our national vessels. And basically, we wanted to characterize the parameters of the coastal current, the structure of the water column in the area, and take zooplankton samples in the current itself and then in the surrounding water bodies, just to make sure that what we were seeing was clear differences. We chose Southwest Ireland for a number of reasons. Mainly, that's where we're based. Secondly, as I said, there's high numbers of Muggaea in that region in recent years. There's also a lot of salmon aquaculture in that region, and a lot of the research into the coastal current has also been concentrated in that region. So we used CTD methods on board to characterize the physical structure of the water column. So that's just pictures of the CTD being deployed into the water column. And we had 14 stations along a 30-kilometer distance, starting inshore at around 30-40 meters depth, moving progressively offshore. Each station was spaced 2 kilometers apart. So we got a really nice picture of the water column. And then what we did was all of these measurements that we got of temperature, salinity, density, we loaded into Ocean Data Viewer, and we built up a physical picture of the water column. And this determined where we did our plankton sampling. We used multi-nets. This multi-net had 5 nets, so we could take 5 separate depth bins, which allowed us to assess not only the horizontal distribution of zooplankton along the transect, but also the vertical distribution within the water column itself. The mesh size was 300 microns, and we collected 76 zooplankton samples across 3 transects, with an average of 77 meter cubed of water filtered per sample. And so we took samples in the current itself, inshore and offshore. Our prediction was that we would get higher abundances of Muggaea in the coastal current waters when we compared it with the mixed inshore and the stratified offshore. So this map shows our Transect 1 CTD data. I only have time to go into one transect, but you can talk to me if you want to know about the other ones. So the orange dots are the CTD stations, and as you can see, we started quite inshore and moved progressively offshore. And this is a section plot of temperature for our Transect 1. So on the x-axis, we have section distance. On the left of the graph is our most inshore station, starting at 0, and as we move right across the graph, we're moving more offshore. On the y-axis, we have depth, and it's reversed. So the top of the graph is the surface, and as you go down, it gets steeper, and it's colored by temperature. So red is 17, 18 degrees, green, yellow is 14 to 15, light blue is 13, and then purple, dark blue is 10 to 12. So if we look at the left-hand side of the graph, we're getting a gradual change in temperature as we go deeper. This indicates we're getting a gradual, our inshore mixed waters. Compared with the offshore part of the graph on the right-hand side, there's a clear band of red, warm water, a rapid change in color, so rapid change in temperature or our thermocline, and then a large band of blue-purple cold water beneath. So that's our bottom density front. This structure is quite typical of the Celtic Sea in the summer. This plot now shows something different. It's geostrophic velocity, which is the directional flow of water, so how fast it's flowing and in what direction. Again, section distance is on the bottom, inshore is on the left, offshore is on the right, depth is on the y-axis and it's reversed, and the color indicates the flows. If you want to know more about the specifics of geostrophics, you can talk to me, but just bear with me. It's the eastern component. Basically, it means if it's a positive value, it's flowing eastwards. If it's negative, it's flowing westwards. So the orange-red are positive, so it's our eastward flowing water, and our green, blue, purple is is negative, so it's westward flowing. So that core of blue in the center of the graph is strongly westward flowing water, and that's what we identified as our coastal current. And these little icons of a multi-net just show where we took our samples, inshore, within the boundaries of the current itself, and offshore. And I just want to point out as well that that band of blue is really only in the top 30 meters, so below that we're getting eastward flowing water again. So for our results, first of all, we were delighted that we got Muggaea in the first place because Damien attempted this a number of years ago and found no Muggaea. And what's more is we found Muggaea in the coastal currents, that top 30 meters. So this was really exciting for us. And what was even more exciting was that there was lower abundances in the depth strata below the current, and it was essentially absent from the offshore waters. Now, we did find slightly higher abundances of Muggaea inshore compared with the coastal current, but I'll come back to that in just a second. And just to show you that this isn't the distribution of all the gelatinous zooplankton, I want to show you the distribution of a typically oceanic species, Aglantha digitale. The distribution is essentially flipped. It's opposite. So we're getting most of the Aglantha below the current and in the offshore waters, with barely any in the current and inshore. So it just shows that the offshore water is really connected with that below the current section, and the current is kind of connected with the inshore waters. So back to our hypothesis that Muggaea atlantica is transported by the coastal current. I'm inclined to accept this. We found Muggaea in the current, and we did find it across our other transects as well. But to our prediction that we would get higher abundances in the current compared with the inshore and the offshore, not quite. Yes, there was more than the offshore, but there was higher in the inshore compared with the current. But when we think about it, the kind of impetus for doing this research was because we were seeing such high numbers inshore. So of course we were going to find some Muggaea inshore. And like a lot of current systems, this current isn't, a hard and fast boundary where nothing gets in and nothing gets out. likely there's loads of small eddies that spin off at various points of the current, seeding and transient in situ population. So that's what we think is probably happening. And just briefly, we've also done some community analysis. So I didn't just assess Muggaea and Atlantha, we looked at the gelatinous zooplankton community in total. And this shows, sorry, I'll just explain. The circles are below the current, the triangles are within the current, the pluses are the inshore, and the X's are the offshore. It's probably kind of hard to see on the screen, sorry. We can see a bit of clustering between the inshore and the current samples, and clustering between below the current and the offshore samples. So I'm pretty confident that there is some partitioning of the gelatinous zooplankton community here. This is still preliminary, so we're not quite sure if these clusters are significant yet, but it's probably a species-specific response for the likes of Muggaea atlantica and Atlantha digitale. For the Physonex siphonophores, we kind of saw a very different picture. But anyway, in our conclusions, Muggaea was found within the current, while of course we can't say it's coming from the Western English Channel at this point, which we would probably have to do molecular genetics to say that. We can say that we're pretty confident it's not coming from an offshore source. So thank you so much for listening to me, and if you have any questions, let me know.